Hello friends. In the video நம்ம என்ன பார்க்க போறோம்னாக்கா இந்த ரீசனா நடந்த கேட் எக்ஸாம் क्वेश्चन பேப்பர்ல லீனியர் அல்ஜிப்ரா क्वेश्चन மட்டும் சால்வ் பண்ண போறோம். இப்போ look at the first question. என்னன்னா suppose that the characteristic equation of the matrix M is lambda cube plus alpha times lambda square plus beta times lambda minus 1 equal to 0, where alpha comma beta are complex number with alpha plus beta is non-zero. Which of the following statement is true? So we know that by Cayley-Hamilton theorem, the matrix satisfied its characteristic polynomial. Therefore, from the Cayley-Hamilton theorem, we know that m cube plus alpha times m square plus beta times m minus identity equal to 0. Okay, so this is we know. Okay, so therefore we can easily check that the last one is the correct option. Why? Because look at the last option, just to multiply m both side. Therefore, the left hand side is m inverse m cancel. We have a m inverse minus beta times identity. And since we are multiplying m both side, therefore m into m square plus alpha times I into m is nothing but m. Okay. Now we take this beta I to that side. We have m inverse equal to m square plus alpha times m plus beta times I. Now multiply m again both side. We have m into m inverse is nothing but identity equal to we multiply m both side. Therefore we have m cube plus alpha times m square plus beta times I into m is m. Therefore if you take this I to this side, we have we get the equation m cube plus alpha times m square plus beta times m minus identity equal to 0. So we get our equation. Okay. Therefore, option D is the correct answer. Okay. Now we look at the next question. Next linear algebra question is this one. So consider there are two statements. M is a m by n matrix with m is bigger than n and n is bigger than or equal to 2. If suppose rank of m is n, then the system of linear equation mx equal to 0 as 0 as the only solution. This is a one statement. So another statement is E is a n by n matrix, a non-zero matrix, but E cube equal to 0. Then I plus E square is a singular matrix. So which of the following statement is true? So we know that m is a, look at the first statement. So m is a m by n matrix. Okay, so that is actually m is a function from Rn to Rm. So any matrix can be viewed as a linear transformation. So since this is a m by n matrix, therefore m is a function from Rn to Rm. Now apply the rank nullity theorem. So dimension of the domain equal to a rank of m plus nullity. Nullity is nothing but dimension of the kernel. So nullity of m. And it is given that a rank of m is n. Therefore n equal to rank of m is given that n. Therefore the nullity should be 0. So nullity is 0 means what? The kernel contains only 0 vector. So that is the kernel of the transformation m contains singleton 0. Because the dimension is 0, therefore it contains only singleton 0. So actually what is the kernel? Kernel is nothing but set of all vector x such that is satisfied that mx equal to 0. And we know we proved that this is nothing but singleton 0. So therefore 0 is the only solution for the system of equation mx equal to 0. Therefore the statement P is always true. Okay. Now P is true. We proved that the statement P is always true. Now look at the statement, second statement Q. It is given that E is a n by n matrix, but E cube equal to 0. So E cube equal to 0 means what? It should be a nilpotent matrix. And we know that all the eigenvalues of a nilpotent matrix are 0. So it's a n by n matrix. So there are n eigenvalue, that n eigenvalues are all are 0. Because we know that every nilpotent matrix, the eigenvalues are always 0. So this is the eigenvalues of E. So this is the eigenvalues of the eigenvalues for the matrix E. And since we know that we know the theorem, if suppose A has an eigenvalue lambda, then A square has a eigenvalue lambda square. You have to square each eigenvalues. Therefore, what is the eigenvalues of E square? You have to square each eigenvalue. That is 0 square, 0 square. That is, but we get always 0, 0, 0. So this is eigenvalues of E square. And what is the eigenvalues of the identity matrix? N by n identity matrix is nothing but 1, 1, 1. Okay, 1. Now, since this identity matrix and the E squares are commutative property sets, that is I into E square is equal to E square times identity. Therefore, that eigenvalues of I plus E square, this matrix is nothing but you have to sum. We have 1 plus 0, that is 1, 1, 1, 1. So therefore, the eigenvalues of the matrix I plus E square is nothing but everything is a non-zero eigenvalue. Therefore, the determinant of I plus M square is nothing but product of the, E square. Product of the eigenvalues is nothing but 1 is a non-zero number. Since the determinant of this I plus E square is non-zero, therefore, the matrix I plus E square is non-singular. But it is given in the statement that I plus E square is singular. Therefore, the statement Q is false, but always the statement is P is true. Therefore, P is true, but Q is false. Option C is the correct one. Okay. Okay. So the next question, I think the next linear algebra question is, we can see. Okay. So next one. Yeah, this one. So let T is a linear transformation from R2 to R2 given by this 1, 2 maps to 1, 0 and 2, 1 maps to 1, 1. Suppose for any PQ in R, suppose T inverse of PQ is X, Y, then which of the following statement is true? Okay. So whenever we talk about T inverse, therefore T is invertible. Okay. Therefore should be 1, 1 on 2. So from this, we conclude that T inverse of 1, 0 should be 1, 2. And from the second condition, T inverse of 1, 1 should be 2, 1. Okay. So if we look at the first case, so suppose if you take P equal to 1, Q equal to 0, you will get X equal to 1 and Y equal to 2. So, so look at this one. If substitute P equal to 1, Q equal to 0, here we get 1 minus 0 is 0. Okay, 1 minus 0 is 1, therefore X equal to 1. Again, if substitute X equal to, P equal to 1, Q equal to 0, we'll get Y equal to 2. Now look at again same thing here. In this case, if you take P equal to 1 and Q equal to 1, you'll get X equal to 2 and Y equal to 1. But if you substitute here, 1 minus 1 is 0, you will get X equal to 0. Therefore, this option is wrong. Okay. Similarly, you can, if you check this here, substitute P equal to 1, Q equal to 1, you'll get Y equal to 3, but we need Y equal to 1. Therefore, this is also a wrong statement. And similarly, the last one also, since P equal to 1, Q equal to 1, we need X equal to 2, but here we get X equal to 0. So therefore, this is wrong. Therefore, again, if you substitute here, we will get that if substitute X equal, P equal to 1, Q equal to 1, we get X equal to 2. And if substitute P equal to 1, Q equal to 2, we get Y equal to 1. This is satisfied. Also, this also satisfied. If substitute P equal to 1, Q equal to 0, we get X equal to 1. If substitute P equal to 1, Q equal to 0, we get X equal to 2. Therefore, the correct statement is the second one. Okay, this is simple. So just you have to substitute the value, you get it. Okay, so the next question, next linear algebra question. Okay, now this one. So consider R3 as a vector space with the usual operation vector addition and scalar multiplication. Now we have given the two subspace W1 and W2. So where dimension of U means dim U means what? Dimension of U. That is a notation. Now we have to find the dimension of V1, V2, and then we have to check which one is correct. Okay. So, and from this, we conclude that in the condition, so actually how many variables we have? X1, x in x3, x in R3 means what? X1, x2, x3 satisfying this condition. So simply we can write x3 equal to x1 plus 2 times x2. Okay, therefore we can replace this x3 by x1 plus x2. Therefore, this W1 is nothing but set of all x1, x2, the third x3 can be replaced by x1 plus 2 times x2, where x1, x2 varies over real. So how many unknowns we have? Only we have x1, x2. Therefore, the number of unknowns, therefore dimension of W1 is nothing but 2, because we have only 2 unknowns, namely x1, x2. This term is a linear combination of x1, x2. Therefore, only unknowns are x1, x2. Therefore, dimension of W1 is 2. Now look at the dimension of W2. So we can rewrite as this x3. X3 is nothing but minus 2 times x1 by 3. Therefore, again we can replace x3 by 2 times x3. Therefore, W2, the subspace W2 is nothing but set of all ordered triple x1, x2, x3, but x3 can be written as minus 2 times x1 by 3, such that x1, x2 are varies over R. Again, here the number of unknowns are 2, only x1, x2. Therefore, the dimension of W2 is also 2. Okay. So now, what is the dimension of? Look at the first option. Dimension of W1 and dimension of W2 are equal because both are 2, 2. Therefore, dimension this. But the question is, which of the following are 2? So therefore, more than one options are right. So first one is always right. Now look at the second option. So this dimension of W1 is 2 plus dimension of W2 is also 2 minus dimension of R3 over R is 3. Therefore, 4 minus 3 is 1. Therefore, this also 2. Okay. Now, we have to find the dimension of W1 intersection W2. So what do you mean by W1 intersection W2? First, we have to take W1 intersection W2 is the set of all ordered triple x1, x2, x3 is satisfying both the condition. So the first condition is x1 plus 2 times x2 minus x3 equal to 0. Okay, so x1 plus 2 times x2 minus x3 equal to 0. Also satisfy the second condition, the second equation, 2 times x1 plus 3 times x3 equal to 0. Okay, so therefore, we can conclude that we got to eliminate the variables. So from this we can take, we have to solve. Okay, so otherwise simply we can say these two are linearly independent equations. Okay, these two equations are linearly independent. So therefore, number of variable is 3 minus number of linearly independent equation, that is 2. Therefore, we have 1. So therefore, dimension is 1. So otherwise, we have to reduce the variables. So from the second equation, x3 can be written as minus 2 times x1 by 3. Therefore, this is nothing but collection of all x1. Okay. The final term x3 can be written as 2 times x1 by 3. Okay. Now look at the first equation. We can write x2 2 times x2 is nothing but x3 minus x1. And if you divide it by 2, we get this one. Therefore, x2 we can write in terms of x3 and x1, but we know that x3 is nothing but in terms of x1. So therefore, this is in terms of, so maybe we can write simply again function of x1 is in terms of x1. So therefore, we have only one unknowns, namely x1. Okay, therefore the dimension of W1 intersection W2 is nothing but 1 because we have only one unknowns in the intersection. Therefore, option D is also right. Now look at the option C. We have to use the formula. We know the dimension of V1 W1 plus W2 equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. This is a standard formula. So this is 2 plus this is 2 minus this is nothing but 1. Therefore, we have 3, but it is given that 2. Therefore, this option is wrong. Okay. Okay. Next question. Okay, maybe this is the last question for this one. It is given that M is a 3 by 3 matrix with a satisfying condition m square minus 2 times m plus 3i. Therefore, the minimal polynomial of m should be x square minus 2 times x minus 3 is the minimal polynomial. Maybe you can take m of x. So we know that all the roots of minimal polynomial are the eigenvalues. So we can rewrite this as x minus 1 into x minus 2. Okay, we will check it. So no, it's actually x plus 1 into x minus 2, because x into x square, and this is minus 2x plus x. Okay, this is 3. Sorry. So therefore, this is minus 3x plus x 2x. Okay, 1 into 3 minus. Therefore, we know that now. So, but this matrix have 3 eigenvalues. But so far we know that 2 eigenvalues. The eigenvalues are minus 1 and 3. And we don't know another eigenvalue. Suppose we take lambda. So because it's a 3 by 3 matrix, all the roots of minimal polynomial are the eigenvalues. So, but this is two second degree polynomial. Therefore, we found 2 eigenvalues. Maybe the another one of the eigenvalue may be a minus 1 or 3. Okay. So, but it's given that the determinant of matrix is nothing but minus 1. So, determinant is nothing but product of the eigenvalues. If you product this, we get minus 3 lambda. It is given that this is nothing but minus 9, because the determinant is nothing but product of the eigenvalues. And therefore, we have to find lambda. So, from this, we can multiply by 1 by 3 and minus 3, we get 3. So, lambda should be 3. So, therefore, the eigenvalues are, the eigenvalues of the matrix are minus 1, 3, and 3. And we need, they asking trace of the matrix. So, trace is nothing but sum of the eigenvalues. So, therefore, sum should be, this is 6 minus 1 is 5. Therefore, trace of the matrix should be 5. Okay, now we solve all the problems from linear algebra. Okay, thank you. We will solve in the next video. We will solve question from algebra. Okay. Okay. Thank you.